Pressure is a fundamental concept in physics and engineering, and understanding it is essential for grasping how fluids behave. At its core, pressure is defined as the force exerted per unit area. Imagine you have a balloon. When you blow air into it, you're applying force against the inner walls of the balloon. The air molecules collide with the walls, and this creates pressure. The more air you add, the greater the force exerted on a specific area of the balloon's surface, leading to an increase in pressure. This relationship can be expressed mathematically. Pressure equals force divided by area. Now let's delve deeper into how pressure behaves in liquids, particularly focusing on two key factors: depth and density. When you submerge an object in a liquid, the pressure experienced by that object increases with depth. This phenomenon can be attributed to the weight of the liquid above it. Picture yourself diving into a swimming pool. As you go deeper, you feel that pressure building up against your ears. This is because the water above you is exerting its weight downwards, and the deeper you go, the more water there is above you, thus increasing the pressure. The relationship between depth and pressure in a liquid is linear. For every meter you descend in water, the pressure increases by approximately 9.81 kilopascals, which is equivalent to about 1 atmosphere of pressure for every 10 meters of water. This principle is crucial for understanding how submarines operate or how deep-sea divers manage their ascent and descent. If a diver goes too deep without proper equipment, the pressure can become overwhelming, potentially leading to serious injuries or even death. But depth alone doesn't tell the whole story. The density of the liquid also plays a significant role in determining pressure. Density is defined as mass per unit volume, and different liquids have different densities. For instance, salt water is denser than fresh water. This means that at the same depth, the pressure in salt water will be greater than in fresh water. If you were to dive into the ocean and then into a freshwater lake, you would notice that the pressure feels different, even at the same depth, because of the difference in density. To illustrate this further, consider two containers filled with liquids of different densities. If you have one container filled with water and another filled with mercury, which is much denser, the pressure at the bottom of the mercury-filled container will be significantly higher than that of the water-filled container at the same height. This is due to the greater weight of the mercury column compared to that of the water column. In practical applications, this principle is vital in designing equipment like barometers, which measure atmospheric pressure, or in hydraulic systems that rely on the incompressibility of liquids. Moreover, pressure in a liquid is isotropic, meaning it acts equally in all directions. This is why, when you open a bottle of soda, the gas inside escapes rapidly and you see bubbles form. The pressure inside the bottle is greater than the atmospheric pressure outside. When you release that pressure, by opening the bottle, the carbon dioxide dissolved in the liquid escapes, creating those fizzy bubbles. In summary, pressure is a critical concept defined as the force per unit area, and in liquids, it depends on both depth and density. As you go deeper into a fluid, the pressure increases due to the weight of the liquid above. Additionally, the density of the liquid affects how much pressure is exerted at a given depth. Understanding these principles is essential not only in physics, but also in numerous real-world applications, from engineering to environmental science, and they help us comprehend the behavior of fluids in our everyday lives.